What's going on, everybody? Mr. Gustin back in the physics classroom. Let's talk today about area of graphs, particularly the velocity and time graph today, but the area besides slope is the other part of the graph that's got some meaning to us. Obviously, there's the function itself, what the curve is doing, and that matters to us. There's the slope of the graph, which is the rate of change of my dependent variable over my independent variable. That means something to us, but we haven't quite analyzed the area of the graph yet, and that's what these notes are about today. So let's look at this area has meaning worksheet on Canvas and see what we can come up with here. So the scenario is a physics student is riding their skateboard in front of the point, and his motion was plotted on the graph below. Okay, so it looks like if I'm going to describe the motion, which number one asks me to do, describe the motion. If I'm going to describe this motion, I think I'm going to say, well, initially they're moving at 3 meters per second for 2 seconds. There's a constant slope there. There's no change. There's no acceleration. There's no slope on the VT graph. So a constant velocity of positive 3 meters per second. Then between 2 and 3 seconds, there is a slope. Their speed or velocity starts to change as it approaches 0. That means they're slowing down from going forward at 3 meters per second, still going forward, but reaching a stopping point. After their stopping point, it appears that they move in the opposite direction because they end up going 1 meter per second in the negative direction or the backward direction or the other direction. So I'm going forward at a constant speed. I'm slowing down, stopping, and then going backward at accelerating at a slower rate than I was before until I reach that constant speed in the backward direction. This is my description of that motion, and it asks me to draw an FBD for each part. Well, for each part, if there's no acceleration, that means there's no net force. So let's start with the easy one. Of course, there's the weight force or gravity, and of course, there's the ground force supporting the student and their skateboards. That's happening there. There are no forward or backward forces because they would be balanced out if they were. So maybe the student's just like on their skateboard, maybe with a slight incline, but probably not. But they're just going forward at a constant speed. Nothing is slowing them down. Nothing is speeding them up. The net force, total force, is 0. For this part over here, as they slow down, we know that there has to be some kind of force acting in the opposite direction because we're going to slow down. Slowing down means that the velocity and the acceleration must be in opposite directions. So I need a force in the opposite direction of motion. So I'm going to, again, start with my weight force and start with my ground force. And the only force I can think of that would slow someone down on a skateboard is friction. So I'm going to go ahead and draw my force of friction, or my FF there. Then, at a certain point, they stop, and that's okay. There's no need for extra forces there, but there's a change somehow. Somehow, this student right here starts to speed up again because now they're increasing their speed, but in the negative direction. So that means they're increasing their velocity. So there must be the velocity and the acceleration in the same direction. So I'm probably still going to see, my ground force and my gravity force, probably still a little friction, but now there's going to be some kind of, let's call it like a push force. Maybe they're pushing with their foot, but there's some kind of forward push force. Maybe they're pushing off the ground to kind of get their skateboard moving again because they reached a stop. So, you know what, folks? I messed up. They changed direction. So the acceleration had better be in the other direction, shouldn't it? Good catch at home, folks. I can hear you through the screen. Their push force must be in the other direction. And so if there is any friction force, it'll be little and it will have flipped directions because I'm going faster in the other direction than I was before. And then I'm going at a constant speed again. So maybe once I'm going at a constant speed, now there's the FG and the F ground, but there's no force acting, and these are going to be equal. They're equal the whole time because we're not accelerating vertically. But now there's no outside force to accelerate me. I'm going at a constant -1 meters per second. So maybe those forces are gone. Maybe they're balanced. I'm not going to model them. I think they're just probably gone. Maybe they're just gliding across some smooth surface. So there's very little friction, and they're going at a constant speed. So these are the 4 FBDs we have for the 4 different parts. There's 1, 2, 3, 4 different types of motion happening here. And so those are our 4 FBDs. You might want to pause here and make sure you had these FBDs down before you move on. Okay? Number 2 asks me to find the acceleration at 1.5 seconds and at 2.3 seconds. And I've got no eraser around here, so that's going to be a problem. Let's just go ahead and erase this. or slide the board this side. Finding the acceleration. Well, acceleration, if I remember right, acceleration is the slope of the V versus t graph. So I'm going to go find 1.5 seconds and 2.3 seconds and 3.6 seconds, and then go find the slope at those locations. So at 1.5 seconds, that's right here. Well, that slope is 0. So my change in speed over time is 0 meters per second, or 0 meters per second squared. At 2.3 is somewhere around here. I need to find this slope right here. And so what is the slope of that line? Well, I could look for that really small point, or I could just say that this whole line here has a constant slope. So I'm going to go ahead and just find the whole slope of that line. So it looks like my speed changes by, it goes down 3 meters per second in 1 second's time. How's it going? Okay, so that's going to be a negative 3 meters per second. That's my acceleration there, okay? And so what I need to do there, that's for 2.3 seconds. The last one's 3.6 seconds. 3.6 seconds is somewhere in this area right here. So if it's there, my slope is going to be, let's see, it changes. How does it change? Well, it goes from 0 to -1. So it actually changes by a -1 meter per second over this 1 second. That ends up being -1 meter per second. And so that's my acceleration at these 3 locations. I'm just finding the slope of that graph. Pretty straightforward. Again, if you want to get this down, you might want to pause this to do so. The last 3 questions ask me about displacement. What is the displacement after 2 seconds? Well, after 2 seconds, let's look and see how fast I've gone. It looks like after 2 seconds, I've been moving for 3 meters per second for 2 seconds. And I know that there is an equation I can use there for this displacement. And so the displacement equation is change in x is equal to velocity times time. We know this, we've seen this, we've done this equation before. So it's a constant velocity. My change in position over, my speed is positive 3 meters per second. The time I was moving was 2 seconds. So my change in x actually is 6 meters. And that's positive 6 meters because I've been moving that way the whole time. I can use an equation to figure that out. That's fantastic. But what happens when I don't have a constant speed? Like, what is the area between the graph from 0 to 6 seconds? Because that's what this is all about. This is about what is area here. So area can be tricky to find on this graph, but area from 0 to 6 seconds is sometimes known as the integral if you're a math nerd. But from 0 to 2 seconds, what is the area bound by the 2 axes and the function itself? If I look at 0 to 2 seconds, the axes and the function, I end up with this nice geometric shape. It looks kind of like a rectangle. I know how to find the area of a rectangle. That's pretty easy. That's base times height. So if I find base times height, the height of this is 3 meters per second, and the length of this is 2 meters per second. If I find the area of that box, the area is equal to 3 meters per second times 2 seconds. And that ends up being 6 meters, or positive 6 meters as well. I'm curious, the fact that this equation here gives me 6 meters, and then the area of this box gives me 6 meters, is telling me something about what the area of this graph might mean. Now, it's very unique to this graph, right? Very unique to the velocity and time graph, but it appears that the area of the velocity and time graph is meters, is displacement. Now, how can I figure that out? How do I know that just by taking the area, it's meters? Well, if I look, kind of like in chemistry class, I've got 3 meters in 1 second times 2 seconds. If I look to cancel out my variables like we used to do in stoichiometry, my seconds cancel out, and I'm left with positive 6 meters. I can look at my units of my y-axis, or my height, and my x-axis, or my base, and I can go ahead and cancel the units out to indicate to me what that area might mean. It's kind of like what we do with the slope, but we divide our units with the slope. And here we're just kind of canceling our units out. So I think the area has meaning. I think I need to make sure I know how to find the area. Again, that's the axes. The axes are two of the bounds or boundaries. The function itself, or the line, the graph, is another boundary. And then time, the time that we're looking at, 0 to 2 seconds, is the other boundary for this rectangle. If I wanted to find, say, the displacement from 3 to 4 seconds, I would say, okay, 3 to 4 seconds is here. There's the function, that's one bound. Here's an axis, that's the other bound. And then right here, the time at 4 seconds would be a third boundary. I would have to take the area of this triangle to find the displacement between 3 and 4 seconds. And notice that area is negative. These are different ways to analyze this graph. I can use slope to find acceleration. I can use area to find displacement. That is unique to the velocity and time graph. All right, get out of here. See ya.